Yes, good morning, good morning, good morning. Oh, not good morning, good evening. Yes, good evening. Okay, so all good, all fine. Audio, video clear. Okay, all things clear. Okay, good. Okay, so what were the things we had done in the last class? What things we have completed in the last class? Yes, CSK. Okay, appearing like CSK today? Okay, good. So, yes, how many things we have done in the last class? Means, what was the last question that we completed? Ice and steam, I think. Steam and ice mixing, okay? Steam and ice mixing was there. And how many questions we did on ice, steam and ice? Steam and ice, how many questions we have done on that part? Steam and ice. Only one, 5 gram with 1 gram steam. Okay, so we'll write one more question on this one. And listen, in case of ice and steam, whenever temperature is more than 100, okay, and you know that temperature cannot be more than 100, so you will answer maximum temperature can be only 100 degrees Celsius. Whenever you are solving the question, any question, okay, like one question is given in the salt example, in any of the question, if you are getting temperature more than 100, which is not possible, so you will answer in that case 100 degrees Celsius only. In that case, total steam will not condense. At this point also I said, if temperature you are getting more than 100, then total steam will not condense. This point was discussed. This point was over. That total steam will not condense. If anywhere temperature is coming more than 100 degrees Celsius, okay, I'm saying now, okay, now I'm saying, okay, like if I say one question, okay, 1 gram ice and 1 gram steam. In this question you will solve, okay, ice 1 gram and you will take here steam also 1 gram, okay, and when you will solve, okay, then temperature of the mixture will be, in this question you will get temperature of the mixture will be 280 degrees Celsius. And when you are getting 280, then you can write, okay, more than 100 not possible. So maximum temperature will be only 100 degrees Celsius. Means if you are getting any answer more than 100, okay, you will answer T mixture is 100 degrees Celsius. If T mixture is more than 100 degrees Celsius, then T mixture you have to answer as, okay, 100 degrees Celsius. In this case, okay, in this case basically, steam, okay, complete steam, okay, complete steam will not condense, okay, means partial condensation will happen in this case, but temperature of the mixture you will write as 100 degrees Celsius. I hope you got this thing. Can you do the calculation for this one? Numerically we can calculate. We can calculate numerically. Okay. So if you are getting more than 100, then you have to answer always 100 degrees Celsius, okay. So now we'll write one more question here, right? A calorimeter of water equivalent, a calorimeter of water equivalent 15 gram, okay, calorimeter of water equivalent 15 gram, okay, means water equivalent for the calorimeter is given. It means you need to consider energy taken by the calorimeter also, okay, contains 20 gram ice at 0 degree Celsius, okay. If some steam, okay, some steam bracket they have given 100 degrees Celsius. If they don't write also, if temperature not given, you have to take 100 degrees Celsius, okay, added, then final temperature of mixture equal to 40 degrees Celsius. Find mass of water in mixture. Find mass of water in mixture. How much water will be present in the mixture? We have to solve in this question. We have to do. So what we can say in this one, this is this side we can write ice, which is at the 0 degree Celsius, and there is the 20 gram. And this is the calorimeter. So we can say calorimeter temperature will be also 0 degrees Celsius. W equal to, we can write ms here, okay. That is given in this case, that is the 15 here, okay. And now we can see we are adding some steam. So ultimately these two are going to absorb the energy. These two will absorb, okay. In this side we have steam, and steam is going to release the energy. Ultimately they have given that finally mixture is having a 40 degrees Celsius temperature, and a mixture is 40 degrees Celsius. Then you know 40 degrees Celsius means pure water will be there. So some steam, this side some steam will be coming, and this side some ice will be coming. So total water will be mass of ice melt plus mass of steam condensed, okay. Mass of audio not clear. Audio, video, fine. Internet, today I think some fluctuations are there in the internet speed. Is it okay? Sir, not clear. Oh. Okay, I think in the, okay, YouTube okay, but in app I think some, okay. Yes. YouTube okay? Audio and video not clear. Okay, then okay, you can just open in the YouTube, okay, you will, okay, maybe in the app, okay, today some problem is there actually, okay. You can just see, okay, in one tab you can open that also, okay, so it'll be better. So we can say, finally we have 40 degrees Celsius, okay, finally you have 40 degrees Celsius, you can just, okay, open in that one and then you can shift there, okay. So 40 degrees Celsius means you have water. So some steam will condense and some ice will melt. Okay, some ice will melt and steam will condense. Ice, 20 gram ice is going to melt, but steam is not given. So we can assume m gram steam, suppose, okay, is condensed in this process. And finally, we have in the mixture 40 degrees Celsius. Okay, so what we can see, ice at the low temperature is going to absorb the energy, and this ice will be converted to 40 degrees Celsius water, okay. This calorimeter also will be converted to 40 degrees Celsius water, okay. Means not 40 degrees Celsius, means calorimeter temperature also increase from 0 to 40 degrees Celsius, okay. And steam will be, okay, steam temperature of the steam is steam will condense into 40 degrees Celsius water. So let's calculate all the energy. Here we can write, this will be first of all MLF, and then we can say MS delta theta. Let's put the values here. We can say M is 20, LF is 80 here, and then we get 20. And specific heat, people are doing the mistakes. You have to be always, okay, all the time you have to cross check here that we are, okay, ice 0 to water 0 and water 0 to water 40. So we are basically increasing temperature of the water. So specific heat we have to take, okay, 1 here. Delta theta will take here 40. So if you calculate, this is the 1600 plus, okay, 800. So this total energy taken by the ice becomes 2400. Energy will be absorbed by ice, okay. And meanwhile, calorimeter will not be, this container will not be at the 0 degrees Celsius. Its temperature also, temperature increases, and finally this, okay, goes to 0, is 40 degrees Celsius. So we can say this one is going to MS delta theta, and water equivalent we know numerically this is the your MS. So we can say that is a 15 into 40. So additionally 600 calories taken by the container here. Okay, 600 calories will be taken by the container. How much steam can release in this process? We can say it will be the MLV plus MS delta theta. First 100 steam to 100 water, and 100 water to your 40 water. So M is not given to us, so we can write 540. Plus we can write here in this one M, okay, S will be basically 1. Again here, water from 100 to 40, okay. So one, and temperature difference 100 to 40, so it will be the 60, okay. So we can write here, this becomes 600 M, okay. So now we can say, sir, 600 M is the released energy, and that side is the total absorbed energy. If you take that side, total absorbed, basically it becomes your 600 and 2400, that are 3000. So we can say heat released equal to heat absorbed, okay. We can write here in this one, heat released means energy released is actually equal to energy absorbed here, okay? And I hope up to this it is clear, up to this whatever written clear na? So you can see heat released is actually 600 amp and heat absorbed this side, okay? I can say 24 plus 6, that actually becomes here. So 20 will be cancelled out of this. We got mH 5 gram. So 5 gram steam is going to be condensed, but answer is not 5. Be careful in the examination what they're asking. They're asking this one final, okay, find mass of water in the mixture. So we can say they're not asking how much steam will condense, they're asking how much water will be there. You can say, sir, mass of water. That water will be actually coming from ice. Some ice will melt, okay? How much ice is going to melt here in this one? 20, and 5 gram steam is going to condense. So final we can say 25 gram will be the water. In questions sometimes they can ask how much steam will condense. They can ask how much water is there finally. So yes, in this case we have 25 gram water finally. Yes. We are ready for the next thing now. Can we move forward? Can we move forward now? Yes. Okay. So after this mixture type of questions are over. Okay. We will be able to do all the questions based on the mixture. Now we'll be doing some more things here. Okay. That will be okay, like we can say when bullet is moving, a car is moving, okay, and you know whenever kinetic energy will be the change, okay, there will be some change in the kinetic energy. It might be due to the friction. These type of questions mainly will be coming in the, so energy released less than energy absorbed. Where less? Okay, in this case final temperature is given. Now how you can say less? Okay, so we can say when final temperature is given, then we can always come to this point. We can say energy released equal to energy absorbed directly. Here mass is not given, so you cannot compare that 600 m is less. M can be anything. Final target is given to you, means you have to come to here. It means okay, all have to come here. So they will take the energy, they will, okay, steam will release the energy, and all have to be, okay, you have to equate. Okay, so we can see like a block, okay, car will be moving, and then because of the friction, okay, speed of the car will decrease. Okay, so we can say this one, work done by friction, work done by friction will be converted to heat. Okay, like these will be the things. Okay, and mainly questions will be coming in the your work power energy. Okay, here we have to do simple things, that yes, kinetic energy, change of Ke can be converted to heat, change of Pe can be converted to heat, and your rotational energy also can be converted to heat. Okay, just basic question, because again detailed questions will be in the work power energy. We will cover how, okay, these things are going to be there. So just okay, basic things we have to relate. Yes, okay, for the heat we have to use ms delta theta or MLF, so that you can get some idea whenever these question appears in the, okay, WP. You can have some ideas. I can use ms delta theta, I can use your MLF, what to use at what time. Okay, so we can say your kinetic energy can be converted to heat, okay, and potential we can convert to your heat, and we can say rotational kinetic energy also can be converted to your heat. Okay, means we can say half of I omega square, this can be converted to heat. It can be ms delta theta or it can be your MLF. Okay, depending on the cases, we can have anything. Half I omega square, it can be ms delta theta, or it can be basically your MLF. Sometimes torque will be given. I'm not taking the questions on the torque and all the things in the detail, because again, whenever you will be doing the WP, okay, then torque and all the things will be at that time in the mechanics you will be having. So it will be easier for us, okay, to relate. Okay, work done by the friction. So work done by friction also can be converted to heat. Okay, you will have this question that, okay, work done by friction. So whatever the losses are there, that will be coming in the form of heat. So basic questions I'm going to take here. So right, this thing is written here. This, okay, right, a bullet moving with speed v. Bullet moving with speed v. Okay, right now speed v is there. Okay. Strikes a target, this is the target here, and comes to rest. Strikes a target and comes to rest. If its half energy is used to heat bullet. Okay, half energy is used to heat bullet find rise in temperature of bullet. Okay, find rise in temperature of bullet. We have to find. Means they are saying that it is moving with the velocity v, and finally whenever it is going to hit the target, then it becomes to rest. So we can see how much change of kinetic energy in this case. You can see, sir, change of kinetic energy in this case is going to be how much? Half of mv square, because here half mv square and here 0. So change of k equal to 0. So now we can say its energy, whatever the change is there, half of the energy is going to heat the bullet, not full. And suppose this line is not given, how much part is used for the heating purpose, then we can assume 100% part. Okay, if they have not specified, we can take 100%. Otherwise they will specify how much part is used to heat the bullet. Okay, clear? In this case means we can say how much heat is generated. Actually heat generated is the half of the energy. Means here change of energy, change in the kinetic energy is basically half of mv square. So half of that is the heat. So we can write heat will be equal to, in this case we can say how much heat is generated. You can say, sir, heat generated is nothing but the half of 50% of this half of mv square. I hope this part is clear here. Half of mv square. Then you can say, sir, h equal to this is just saying, in this case for the heating purpose I'll be using only ms delta theta. So mass will be cancelled, and delta theta we can say this becomes v square divided by 4s. I hope this one is clear. Yes. Okay. Then now if they are giving numerical question also, okay, then you can just put the value, like I can say v equal to suppose 100 meter per second. In a specific heat they have given suppose, okay, 400 joule per kg degree Celsius. So you can just put the value, sir. Delta theta is going to be nothing. V square means your 100 into 100 divided by, we can say 4, and s is basically here 400, and then you can calculate these two cancelled, and this is the your 25 by 4, so 25 by 4 degree Celsius. Yes. Any problem here? Can we do like this? Numerical. But remember, here in these questions, you know, K, P as well as rotational energy. All the time, these energy will be in the joule. These energy will in all these energy will be in joule. Okay. And if all the energy are in joule, then it is better to solve these questions in the SI unit. Okay. So till now, full calorimetry is over. We have done in the calorie, but for these questions, okay, for the KP and rotational related questions, we will prefer to solve these questions in the SI unit. Okay, we will prefer to solve in the SI unit. Clear? We'll prefer on the SI unit. Yes. Clear? Okay. So can we do next question now? Again, kinetic energy, potential energy, and rotational energy you have to prefer in the which unit? SI unit you have to prefer. Okay. Yes. Okay. Kusuma, what you asking? Ice block on ice? Ice plus ice already we have done. Ice part is over. Which one you want to ask? Be specific. Okay, what is your doubt? Sometimes you are not specific. Okay, you need to tell the exactly here is the problem. Okay, whenever you, okay, you are going to be, okay, doctor after some time. Okay, so you need to tell. Okay, you will go. Okay, you will ask like this. Okay, pain is there, but where pain is there? Okay, here, where? Okay. In that one numerical not there. Syam, in that one numerical is not there. There is just one theoretical point. Okay, nothing else. Okay. Right now we are doing the numericals. Okay. Okay. Whatever I am understanding of that thing, I will. Okay. Ice on block. Ice on block. Okay. Ice on block. Yes, we will do. Okay. We will do that question. Don't worry. Okay. It will be done. Okay. 100% that will be done. Okay. That hailstone also we are going to do. Okay. Next question we are writing here on the potential energy. Okay. Right. A block of mass 10 kg released from height 50 meter. Okay. A block of mass 10 kg released from height 50 meter. Find Number one, heat generated, okay, when it reaches, okay, surface of earth. Okay, when it reaches surface of earth, then how much heat will be generated? Means if you picturize this problem, you can say, sir, it is like this. We have this block of okay, this is a block, and when this will reach surface of earth, how much heat is going to generate? You can say, sir, heat will be basically coming in this case from the change of potential energy. Here potential energy is mgh, and here potential energy we can take as 0. How much change is there? You can say, sir, change of potential energy is how much? Your mgh. Okay, change of potential energy mgh. Yes, can I say like this? Change of potential energy mgh. And here h is not very large. Okay, h is not very large. Okay, h means just like, okay, yes, 5 kilometer, 10 kilometer, 20 kilometer, 50 kilometer this way. Okay, not very large as compared to the radius of earth. Okay, in the gravitation, because we'll so okay, change of potential energy, then I will say something else. Okay, so we can say, okay, mgh, and we can say heat generated. In this one, they have specified how much part is converted into heat, and they have not given anything, so we are going to assume 100% part is converted into heat. So we can say heat is going to be equal to mgh. Okay, and let's calculate this value. So you can say how much heat will be generated. 10, g will be 10, and this is the 50, so we can say h becomes here in this one 5000. Okay, joule energy is generated. Okay, 5000 joule energy is generated in this question. Okay, sometimes they can ask, and again I am saying that prefer K, P and R, okay, these questions in the SI unit, much better. Okay, they may ask now in calorie. If they're asking the calorie, now we can change. Okay, we will get answer all the time in the joule. Now we can change. Okay, so now you can say, sir, it is basically in the joule, and we can convert by dividing or multiplying. What I have to do? Again here also, okay, some people are doing the mistakes. Into by means with the 4.2, what I have to do? This thing is there. So we can say we can write 5000 divided by 4.2 calorie. Okay, so we can get answer in the calorie as well as joule. Again, you don't have to do exact calculation. You can be, okay, you can do the approximate calculation. 4.2 means 5000 by 4 means approximately answer will be your around 1200. Okay, something. If options are very close, then you need exact calculation. Okay, now then I will ask second part of the question. Okay, in second part they will say that okay, this block disturbs 2 kg water, find rise in temperature of water. Means what are the situation? Basically, if I say, okay, that this is the block. Okay, here we have 2 kg water in this one. Suppose we have some wheel or something. Okay, like this is the one. Okay, here we can say wheel or turbine, something in this one. Okay, like this is the system here. So what will happen? This block will fall, okay, on this one. Then okay, wheel will rotate. So we can say energy of this mgh will be given to this one. This will be basically converted into rotational energy. Finally, this will rotate, and this will supply energy to this water, 2 kg water. Ultimately, we can say, sir, energy of this, okay, 10 kg is directly given to this 2 kg. Okay. And if you say any loss, then whatever the loss happens, that loss will be again in form of heat. Okay, loss will be again in form of heat. So directly we can say that this block disturbed with this 2 kg mass, means energy of this one is given to this 2 kg mass, because of that temperature will rise. Okay, so here we can say this one. Okay, sir, with this heat, there is the 5000 joule. Okay, your water temperature will rise. So we can write ms delta theta. How much? Okay, What mass is disturbed? We can say 2 kg mass is disturbed. Okay, 2 kg. So I can write here 2. S will be 4200. Okay, again I'm doing in the SI units. So 4200. Delta theta we have to find equal to 5000 here. Okay, then we can say 2020 will be cancelled, and finally we can say this will be the 25. So we can write delta theta becomes here 25 by 42 degrees Celsius. Okay, this is the rise in temperature of water. Okay, ready for next question now? This one is clear, because this water is okay, this block is going to disturb, means energy of this block, whatever the energy is there, that is given to 2 kg water. Okay, by whatever the means, and we can use ms delta theta for that. Okay, yes. So we are having next question now in this one. So in this one, this is that we have used ms delta theta. Okay, so I will take next question here. They will say ice, okay, ice block. Okay, ice block temperature not given, will take 0 degrees Celsius, falls from height h. Okay, falls from height h. Okay, on reaching surface. Okay, now it is falling from height h. So we can say how will be the change of potential energy? We can say simply it will be mg h. And now in this case, this potential energy will generate the heat. Sir, when we will use 4200, 1 calorie per gram. I told in the first class, basically this thing that a lot of people get this doubt. 1 calorie per gram means when we are solving question in the calorie and gram, we have to use 1. I'm saying in the KEP questions, most of the time we will be having energy, because kinetic energy and potential energy will be always coming in the joule. So when coming in the joule, we have to use 4200, because what is the unit for water? 4200 joule per kg. 4200 joule per kg and 1 calorie per gram. So if you are solving the calorie gram, use 1, joule kg, use 4200. Okay, better. Listen, in this previous question, if I want to use 1 here, then I have to solve this one, and this division will take some time. That's why directly I have taken 4200 here. Okay, and I solved complete question in the SI unit. So we can say in this case how much heat will be generated. If nothing is given, okay, if nothing is specified, you will take okay, total potential energy, change of P as the heat generated. Otherwise they will tell 50% heat is converted to, means 50% energy converted to heat, 80% converted to heat. If nothing given, you have to take full conversion into heat. Okay, so we can say H equal to mgh. Okay, now with this heat, ice will melt or it will increase the temperature. With this energy, what is going to happen? Ice will be increasing the temperature or it is going to melt? What is going to happen? Yes, melting or increasing temperature. We can say 0 degrees Celsius ice cannot increase temperature, because maximum temperature of the ice is going to be 0, so it is going to melt. And for the melting purpose, we are going to use here your MLF formulas. We can see this H must be equal to, in this case, there is the M-LF. Okay, total ice will melt. Are you sure total ice will melt? Total block will melt? No, we are not sure total block will melt. Maybe sometimes 10% will melt, 20% may melt, 50% may melt, but I am not sure that 100% will melt. So I have taken here that M-LF. Okay, M-LF. Okay. Now, sometimes they will ask how much ice will melt, and how much ice will melt. We have to find this M-dash. So we can say, sir, M-dash equal to mg divided by LF. First question. In this one, 4-5 questions are there. Okay, we cannot write 4-5 questions separately. So I'm telling, one time they are asking M-dash, so we can say mg by LF. We can calculate. In this question, I'm saying that if okay, on reaching surface, if 10% ice, 10% ice means basically we can say 10% means how much part? 1 by 10th. 10% ice means 1 by 10th. Okay, 10% ice melt. On reaching surface, 10% ice melt. Find height. Okay, you need to find H here. 10% is only melting, 1 by 10th is only melting. So we can say in this one they have given how much is melting, find H. So in place of M-dash, actually what I have to put here? I have to put in this case M by 10, means 1 by 10th of the initial mass. Initial mass I have taken as M. So 1 by 10th means M by 10 into LF will be equal to mgh. So you can say some mm will be cancelled. So from here we can say it becomes LF divided by 10g. Okay. Now sometimes they ask answer this format. If they're asking answer in this format, then very good. Okay, because we don't have to do any calculation. Our answer is ready here. Okay. Quite simple question. H equal to LF by 10g. Sometimes actually what happens that they are asking, okay, fraction of ice melt. Okay, this is another question they can say. Sometimes they can ask mass, how much a mass will melt. Okay, they can say fraction of ice melt. In the same question they can say fraction of ice melt. See, if they are asking fraction of ice melt means whatever will melt divided by initial. Okay, this fraction of ice melt is actually nothing but the m dash by m. Melt by initial. Okay, means m dash divided by m. Melt by initial, that will be equal to melt divided by initial, that will be equal to how much? Melt divided by initial means you can say from this one we have to, this is our main formula, and from here we can say m dash by m will be equal to what's your GH by LF. GH by LF. So we can say this is actually equal to GH divided by LF. Yes? This is clear, na? Fraction of okay, they can ask fraction, they can ask percentage. If they're asking percentage in this particular question, percentage given to us. If they're asking percentage, then we can multiply here 100. Okay, we can say, sir, this m dash by m, from here I'm writing m dash by m will be equal to g into h divided by LF, and for the percentage I will multiply just with 100 here. Yes, clear? Okay, you can say, sir, in this one what value? Suppose they are not asking in this format, they are asking numeric value. They are asking what is the numeric value of h, then how to put as LF? What value how to put as LF? You will say, sir, 80 I cannot put, because I'm saying that whole question I'm doing in the SI unit. Actually your LF is how much? LF is 80 calorie per gram. LF is 80 calorie per gram, but this one I cannot put here. How to use in the SI system? So we can say, okay, 80 calorie per gram actually. So we'll convert this one into joule system. So 1 calorie will be 4.2 joule divided by gram is basically 10 power minus 3. So we can say this becomes here 10 power minus 3 kg. 1 gram is 10 power minus 3, I think. We are clear with this thing? 1 gram is 10 power minus 3, na? No, we don't know. Okay, so we can say 1 calorie 4.2 joule, and this is the your 10 power minus 3. So we can say if you multiply 18 to 4.2, actually becomes here 336. This will go upside, so it becomes 10 power 3 joule per kg. Okay, so this is the value that you have to use all the time whenever you are solving the question. So we can say LF becomes here, I will put 336 into 10 power 3 divided by, I can say 10, G becomes here 10, so you can say, okay, SI system you have to follow here in the KEP questions. So you can say this becomes 3.36 into 10 power 3 meter, or I can write kilometer. Okay, this is the height from which it is falling. Okay, can you write the next question? Next thing in this one, next pattern. Actually, calorimetry is very small topic, but a lot of varieties are there. So many varieties of the questions we have to do. If you say very small, okay, in track sheet also just okay, 3 means 2 or 3, I think 2 lectures are there, just that's it. Okay, but if you don't write that much variety, then what happens, you will not be able to picturize the things. Okay, so we have to do, okay, some more questions in the P again. Okay, potential energy, some more questions. Ready? Listen, if I say in this case, okay, if I say that 1% of ice melt, if 1% of ice melt, then what will happen in this case? 1%. Right now I am saying 10%. If 1%, then what will be the change? You can say for the 1%, sir, only change is going to happen here. Okay, here M by 100 and M by 100. So here also LF by 100 G. Yes, LF by 100 G, na? 1% means M by 100. 1 by 100. So we can say that will be L by 100 G. Can I say that question as homework? Can I give you that question as homework? We will do. What homework? Already I said, na, LF by 100G is the answer. LF by 100G. Just, okay, I can write the type of question, okay? So, I will write in the next page. But remember, here people do mistake of the LF. Lot of people are putting value of LF as 80. 80 is correct, not wrong. But that 80 is basically the calorie and the gram system, okay? And here you have to use the whole thing we are doing in the SI. So that thing you have to convert, okay? So I will say here, next question. Okay, hailstone falls from height h. Okay, if 1% melt on reaching surface. Okay, 1% melt on reaching surface. And again, I'm saying in any question, I'm not writing full language. I just write the main lines of the question. Okay, so here I have just written the main line. Hailstones fall from the height h, 1% melt on reaching surface. You can say, sir, this thing m dash LF will be actually equal to mgh. M dash you write, sir, m by 100 into LF equal to mgh. And I hope you can do this question now. Yes, yes, we can finish this question. H becomes in this case your LF divided by how much? Your 100 G. Okay, we can put the values, we can get the answer here. Ready for next? Okay, so listen, rotational type of question, work done by friction, work done by means frictional loss will be converted to your heat, torque related question, moment of inertia related questions, okay, it will be completed in your WPE part, okay. So not going to that extent, okay, because just starting now, a lot of people may not be having idea also what are the moment of inertia for this spheric, okay, solid sphere or hollow sphere or like this. So I'm not going for that. In WPE we are going to cover those things, okay, frictional losses and all the things, okay. But you know, wherever any loss happens, that loss will be in form of heat, okay. This is the key point that you have to remember. Any loss, it happens in form of heat, and then we can say either we can use for the ms delta theta or mlf, okay. So, right, some of the questions that we'll write here related to the power, okay, related to the power, okay. So we can say in this one, power of a heater is 1 kilowatt, okay, power is 1 kilowatt. And now you know that all these devices are not the ideal devices, okay. These are not the ideal devices. So what will happen, basically some losses are always associated with these losses, okay. Rated, we will be having some rated power. Rated power means that is the ideal power. We are not going to use that one, okay. In the some losses are there, and meanwhile you know that your heater is quite open, so in the surroundings some losses always associated. Its efficiency is not actually 100%. If they are not given anything, we are going to take 100%. We'll assume the ideal cases. But if they have given efficiency like this, okay, power is 1 kilowatt. Okay, they have given 1 kilowatt means we can say this is the 1000 watt. Okay, and we can say 1000 watt means we can write your joule per second. So in per second 1000 joule generated, but 1000 joule are we able, okay, are we going to use? Practically 1000 joule will not be using, because some losses are always there, and the surrounding losses will be there, okay, and whatever losses are happening in the surrounding, that we cannot use, okay. You can say some losses you said in form of heat, but that is going to the surroundings, so that one we cannot use. So suppose if I say in this case 100 joule per second loss is there, so how much will be the usable for us? If 100 joule per second, we can say usable power will be only 900. 200 loss is there, 800, 300 loss, 700. Sometimes these losses I can give in terms of percentage. 80% efficiency. If 80% efficiency, then we can say that 80% of 1000 means 800 will be the usable power. We can say 50% efficiency. We can say 50% will be the usable power. 20% efficiency, we can say your 20% of 1000 will be the usable power. As per the question, whatever they have given, we have to take. So now we can say this one that okay, energy loss to surrounding, okay, to surrounding is 160 joule per second. Energy loss is given 160 joule per second. So we can say actually in this case usable power, okay. One question I will take on the efficiency also, okay. In this question I am taking here directly loss, and one question I will take 80% efficiency, 20% efficiency, okay? So energy usable power, we can say it will be basically 1000 minus 160, that actually becomes in this one how much? 840 joule per second. That is the usable power here, okay? They're asking find time required to heat, or time required to increase temperature of 1 liter water, okay? Whenever I say now 1 liter, okay, 1 liter means basically 1 kg. 1 liter water from 27 to 77 degrees Celsius. Okay, 1 kg, 1 liter means 1 kg, 1 ml means 1 gram. For water, 1 ml means 1 gram. And 1 liter means 1 kg, okay? Because water density is going to be 1 in the CGS. So we can say it is going to be 1 liter means basically your, okay, 1 kg, and 1 ml means 1 gram. So we can say usable power is this, 840 joule per second. In 1 second, okay, 840. So we can say in a t second, 840 into t. And already we know Q is energy generated is power into time. So we can say in t second, suppose t second time is taken, that 840 t joule will be generated. If we are taking t second, then how much energy will be generated? 840 will be generated. So we can say 840 into t, okay. You know, this Q must be equal to MLF or MS delta theta. This Q should be equal to MLF or MS delta theta. We can say this should be equal to MS delta theta, because this energy is only going to increase the temperature. So we can write, I hope this part is clear. Okay, energy equal to power into time, or we can simply say in 1 second 840, in t second 840 t, and this one we can say MS delta theta, and you can write, sir, M in this case is, okay, this is in joules, so whole complete question I am going to do in the your SI system. 1 kg is, I will take 4200, delta theta 2777, that is your 50, equal to, we can say 840 t. Now we can say here 1010 cancel, using 420, we can say sorry here 10, and here we can say 2, okay, yes. And then we can write here t actually becomes in this one, if you see, okay, how much here? 2 if you divide, then how much here? 250, okay, 250 seconds. Any problem in this one? Here 250 seconds. Sometimes they can ask in the minutes, means you say 250 and 60, if you divide 4 times you can directly divide. So it is the 4 minute and 10 second will be left. So 4 minute 10 second will be the time in the minute, okay? 4 minute, 4 directly we can divide, na? 4 times. So 4 minute and 10 second. Ready? Can we do next question now? Next one. Okay, so 2 more questions we have to write on the, one question on the geyser actually, on the same principle. But first I'm, okay, going for one more concept, then I will come back, okay? I will come back for these questions at the, okay, at the last. I will go for one concept now, okay? Right, heating of, okay, heating of solid, right here, heating of solid, okay? Right, this heading, heating of solid, okay? Now, whenever we are going to heat any of the solid, then what happens basically, okay? First of all, okay, heating of solid is the heading. So here, this is the one experiment you can see. We are going to plot, okay, this graph, and this graph is actually between Q. Q on the x-axis means this is the heat, energy on the, okay, we can have taken on x-axis. And here we have taken temperature, okay, temperature on the y-axis, okay. So at point O, we have any of the solid here, okay, at O. If you keep on heating the solid, then solid will keep on increasing the temperature. And at point A, it becomes superheated solid, okay. So at point A, it is the superheated solid. What the meaning of this superheated solid? That more than this, we cannot increase the temperature. Superheated means full. More than this, you cannot increase the temperature. Beyond this, if you cannot increase the temperature, then what will happen? You can see, sir, now phase change will start. So at A is the point at which phase change will be started. So we can say superheated solid, you cannot heat further. So here phase change will be started, and temperature at which phase change will be started, we can say this is known as your melting. Means temperature at which it will start melting, known as melting point. And then at point B, it is completely converted to liquid. So we can say at B actually, this becomes here absolute liquid, okay? At B, this becomes absolute liquid, means completely in the liquid form. You cannot, okay? Means now if you are heating, here temperature is constant, already told to you, during phase change temperature remain constant. Complete liquid is coming. After that, if you are giving the heat, again temperature will keep on increasing. So we can see at point C, this becomes basically here your superheated, okay, superheated liquid. Superheated liquid means you cannot heat further. At C, this becomes superheated. You cannot heat more than this. What will happen? At C now, it is ready to vaporize, ready to convert into your vapors. So we can say here, okay, vaporization will start, and we can say at the point D, it is completely converted into vapor, okay. So this is the absolute vapor here. And now we can say in this one, okay, at temperature at which this will be starting, that is known as your boiling point, okay. If I say at a solid and B liquid, so between A and B, there is the solid as well as liquid, both will be there. Okay, we can say at C, between C and D, liquid and vapor both will be there. At D, absolute vapor. After that, we can increase temperature of vapor also. Okay, so if you say that we got here two types of line, one is the horizontal line and one is the slanted line here, means this one is the line with the slope. So if I say line with the slope represents, you can say, sir, this one is going to represent heating. Heating means formula ms delta theta. Heat we have represented on the x-axis. We can say, sir, here to here heat is going to be ms delta theta. And here to here heat is going to be your MLF. Okay, means this horizontal line represents your phase change. Horizontal line represents phase change. Okay, can I write this conclusion that horizontal line, what horizontal line represents? You can say, sir, horizontal line represents, okay, horizontal line represents phase change. Okay, horizontal line represents phase change. Yes. You can say again, this will be the ms delta theta, means actually this will be here to here energy will be ms delta theta. This will be the MLV, and this is ms delta theta for the vapor. Okay. So horizontal line represents phase change, and you can say, sir, this energy here to here, this energy is actually, okay, this energy is basically equal to the MLV, means this length is actually proportional to this MLV. Mass is constant. So we can say length of the line here we can say is going to be, okay, length of line, okay, length of horizontal line, okay, to be specific, length of horizontal line, okay, length of horizontal line, okay. Less space, I'm writing this one is horizontal written, okay, horizontal written is proportional to latent heat, okay, latent heat, okay, latent heat, okay. And this one you have to remember, practically what we got when we are doing this experiment, that this length was more, so we can conclude that LV is more than LF, okay. And we know practical data also that yes, LV is more than LF because LV is your 540 and LF is 80. Okay, so this is about your horizontal line. Okay, if I say I'm suppose heating solid, it's solid to liquid, then how many horizontal lines should be there? Solid to liquid, how many horizontal lines should be there? You can say, sir, one phase change, one horizontal line should be there. Liquid to vapor, if I say liquid oxygen heated, then how many horizontal lines should be there? If liquid oxygen is heated, how many horizontal line? Means your graph should be having only one horizontal line, because you know liquid to solid there is going to be only one phase change, one horizontal line. That graph will be correct graph. Okay. If I say that suppose I have, okay, dry ice. Dry ice means basically your, or not dry ice, suppose, okay, I'm saying suppose anything is solid, okay, suppose solid is there, so solid to gas, we can say solid to gas, there will be the two phase change, two horizontal line we have to consider here. Okay, now if I say slope here, so we can write slope, okay, slope is basically you can say tan theta, that is also your dy by dx, okay, slope is always dy by dx. We can say on the y-axis, we are representing your temperature, so we can say d theta, on the x-axis dq, so we can say d theta divided by dq, and dq is how much? Your ms d theta, slope dy by dx. Okay, So dy will be d theta by dq. So d theta by ms d theta cancelled. So we can say slope, okay, slope is actually equal to, okay, all the time 1 by ms, or we can say 1 by heat capacity. So you remember, slope of this slanted line actually represents heat capacity, okay, it is inverse of heat capacity, okay, is equal to inverse of heat capacity. Can I say this thing also, that slope, okay, if I write this thing, slope is, because mass is constant, so slope is inversely proportional to specific heat, okay. Can I say this thing? Slope is inversely proportional to specific heat, okay. Any problem here in this one? Completed? Okay, so can we go for questions now? Can we go for questions? Okay, so we'll go for the questions here, okay. So you remember, length is always proportional to latent heat, okay. So I'll be asking questions here. First question that I'm going to ask, okay, they have given one graph, okay, and here in this one, this is the theta, and this is the q, and they have given like this, okay, and they have, okay, given A and B. So in this case, if I say which line is having more length, of course, clearly visible B is having more length. B is having more length, okay? So which will be having more latent heat? More latent heat for A or B? A or B? A or B? Latent heat is more for A or B? Listen, here in this one, till they don't give information of mass, we cannot actually tell this thing. Length of line is equal to ml. Length of line is equal to ml means for A and B, they have to give same mass. Otherwise, you cannot say. Mass must be given here, same mass. If they are giving same mass, then only we can say, okay. Now I have given same mass, we can say, sir, LB is more, okay. Now we can say LB is more, clear? But this point must be given that mass is same, otherwise data is insufficient. I hope you are getting. Second, I can ask same thing, SA and SB. So we can say SA and SB, for A slope is less, and if slope is less, specific heat will be more. Inverse relation is there. So we can say here, in this case, we can say SA will be more than SB. But again here, mass must be given same mass, okay. So if mass is not given, you can say data insufficient, okay. I hope this one is clear. Okay. So now we'll go for next one here. These two, okay. If mass is not given, then we can say data will be insufficient here, okay. They are saying heat is supplied to a solid sample of mass 5 kg at rate of 20 kilojoule per minute, okay. Heat is supplied to a solid sample of mass 20 kilojoule, means 5 kg mass at 20 kilojoule per minute. And they have given the graph. And this graph is given in the question here like this, okay. This graph is given to us. Here theta and here time they have given. Then this time is given in the minute, okay. Here they have given 0, then this is the 1, this is the 2, and then they can say this is the 3, then here we have 4, and here we have 5, okay, like this, okay. They are asking in this question, find two things they are asking. Find latent heat, okay, and find specific heat. So first we can say in this one, okay, this process, and here temperature is given -5 degrees Celsius, and here temperature is given 15 degrees Celsius, okay. Now this process is happening for how much time? ms delta theta, and this ms delta theta is happening for how much time? From the graph you have to figure out this thing, that ms delta theta is for 1 minute, for 2 minutes, for 5 minutes. How much time here, ms delta theta? Because this thing, if you are not able to tell correctly, then you cannot solve the question. So ms delta theta is starting from this 0 to how much time? You can say, sir, 2 minutes. ms delta theta is for 2 minutes. 2 minutes, okay? In each minute, how much energy I am giving? Each minute, how much energy I am giving? 20 kilojoule, okay? Each minute I am giving 20 kilojoule, okay? Each minute I am giving 20 kilojoule, and this is happening for the 2 minute. So we say 2 into 20 will be the total. In 1 minute 20, so in 2 minutes, 2 into 20 kilojoule, okay? S I have to find, okay? S I have to find. So you can say mass is given 5. S I have to find temperature. You can say temperature is sort of minus 5 to 15. And minus 5 to 15 means how much? Minus 5 to 15 means 20. So delta theta is 20 equal to, we can say 2 into 20. Now we can cancel this 20. So we can say, sir, a specific heat becomes here 2 by 5 kilojoule per, okay, kg. I hope this thing is clear. MS delta theta is for 2 minutes, and per minute here given 20 kilojoule, okay, per minute. So we can say that 2 minutes, 2 into 20 should be equal to MS delta theta. Mass is 5 as delta theta. Minus 5 to 15 is your 20. So we can say 20 cancel and we got 2y, okay. If I say second ml, so we can say this MLF process is happening for how much time? From 2 to 5, you can see this is happening for 3 minutes. MLF is for 3 minutes, so we can say 3 into 20, okay? MLF is for 3 minutes, 3 into 20, so we can say mass is given 5, so 5 into LF equal to 3 into 20, so now we can say this becomes LF actually equal to here, so this becomes how much? Your 5, 4, and this will be your 12, okay, kilojoule per kg, okay? Here we have per degree Celsius, kilojoule per kg. Both are clear now? Like this, we have to do questions of graph, okay? Any question coming on the heating curve. This one, some people say heating curve also, or we can say heating of the solid. Can we do these things? Yes? Okay. Now listen, we'll do the next question. Next one. Okay. Right, next thing here, phase diagram. Okay, right, next one here, phase diagram. Phase diagram, okay, right, plotted between pressure and temperature used to find effect of pressure, okay, on melting point and boiling point. Means this is the complete theoretical thing. If I change the pressure, then melting point and boiling point, okay, melting point and boiling point will increase or will decrease, okay. So, okay, we can remember using this phase diagram, or you can mug up also, that is your choice. So listen, what happens when we are, okay, plotting this curve? This one we are writing for the water, means H2O, and this is specific to different material. You cannot mug up for all, so only for water you have to remember. So when we plot, actually we get a graph like this, okay. This is here pressure, and here we are getting the temperature. Then we can write like this, okay. Means, what happened? Okay, so we can say here in this one, this is, okay, we get this type of graph here, okay. Now we can see at the low temperature, okay, this side we have ice here we have water, at the high temperature we have steam. Actually, we are doing these practicals at the, okay, first we are doing for the ice and water. So we get this graph, basically this type of pattern for ice and water, and we can say this one is basically known as melting curve, okay. This part is known as here melting curve, okay. This represents your melting curve, okay. And we can say water to steam. So this one is known as basically your B, means we can say this one is actually your boiling curve, okay, boiling curve here, okay, and we can say this one is your S, then your sublimation curve. So these three graphs we get separate, okay, and all these three graphs when put together in a single graph, when we all are putting in the single graph, then they meet at this point, and this point is basically known as your triple point, okay. This is known as triple point, and what the triple point definition, okay, at which, okay, at which all three is okay, at which okay, we can say okay, all three states, okay, solid comma liquid and gas coexist, okay, all three coexist. That is the basically your triple point. Here temperature is actually 273.16 Kelvin, you need to remember, or we can say in the Celsius 0.01 degrees Celsius. Temperature so many times we have to use, so you remember. But pressure value also you need to remember. This triple point is the condition not for the temperature. You need to specify pressure also. If you are only saying the temperature, it is not actually correct. We need to tell pressure as well as temperature, both the things. And here, pressure value is actually 4.58 mm of Hg, okay, mm of Hg, or we can say in the Pascal, approximately, this is the 611 Pascal, okay, approximately 611 Pascal in the your, okay, in the Pascal, or we can say 4.58 mm of Hg, okay. So these are the two information that you have to keep in the mind. First thing we can say, we have to remember this thing, what are the, okay, this, okay, temperature, and what is this pressure, 4.58 mm of Hg, or around 611 Pascal. What are the uses of this one? I can say here, if I increase pressure, okay, for the melting point, you can say, sir, for the melting point, this is the graph, okay, and for this graph, you will see, sir, if this is the graph, this graph is direct graph or inverse type? This one. If I increase pressure, so if I increase pressure, then temperature is decreasing. This graph is the direct or inverse type? Inverse type. So if I increase the pressure, then melting point will decrease and vice versa. And number two, if I say that if I increase pressure, okay, for the boiling point, so we can say for the vice versa also valid. Is pressure decrease, melting point increase, inverse relation. And for boiling point, if you say, we can say this is graph is there. If this graph is direct or inverse, you can say this graph is the direct type. This one is the direct type, means we can say pressure more, temperature more, means we can say your boiling point will be more, okay, and vice versa also, P less, and we can say here boiling point also less. Yes, correct. Over. So this is the one main conclusion that you have to keep in the mind, okay, this thing, these three things here, okay, pressure, temperature, and this one, okay. Now, one question I will say based on this, that okay, you okay can remember here sometimes, okay, anyone can make the question. Can I do questions? Okay. They will say at triple point of water, at triple point of water, keeping, okay, number one question, keeping temperature constant, okay, two questions they ask, at triple point of water, keeping temperature constant. So what I can do, I can increase the pressure and I can decrease the pressure. And number two question they will say, keeping pressure constant, and here also we can say two things we can do, temperature increases and here we can say temperature decreases, okay. So these are the two things at triple point of water, keeping temperature constant, pressure more, pressure less, keeping pressure constant, temperature more, temperature less. What actually you will get? You can say, sir, this is the graph, okay, this is the graph, okay. And now I can say like this. So here we have ice, here we have water, and here we have steam. First question, if you say, they are saying, sir, keeping temperature constant. Temperature constant, if I put line like this is a line of temperature constant. Yes? And this is the line of temperature constant now. So now in this temperature constant, if I increase pressure, you are right now here, so where your equilibrium will move. If I increase pressure, then your equilibrium will be moved towards, because at the triple point all three are there, your equilibrium will move towards what you will get, water, steam or ice, because your equilibrium will be disturbed. What we are going to get? Temperature constant. If I increase the pressure, what I will get? Ice or water or steam? What how to get here? We can say, sir, if I increase the pressure, I am going to get, I will be in this zone. So what I'm going to get here? I'm going to get water here. Sometimes they will say, sir, if pressure decreases, then what you are going to get? Pressure decreases, then we are going to get the steam, means your equilibrium will be shifted towards steam. If you are changing the conditions a little bit, things will be changed. And we can say, keeping pressure constant. Keeping pressure constant means, I will just say, this line is basically pressure constant line. This is the pressure constant line, and in this line, if I from here, okay, triple point, if I increase the temperature, then I'm going to get the steam here, and if I decrease the temperature, then okay, we will get basically ice. These all three are there, but if you disturb a little bit, then your state will change. Okay, so we can say temperature decrease, ice. Temperature more, steam. Can we do these type of questions? Yes. In phase diagram, this is the maximum things we can do. Okay. So someone was asking, sir, block on ice. One question is there in the material. Can you tell that question? One question on that one. Okay, so this is the one important thing, but generally we are not asking. Okay, so you have to keep in mind that if we change the equilibrium, we disturb the equilibrium, what happens? Okay, yes. Okay, so one question is here. Okay, I will write here question. Okay, in this one. Meanwhile, if you are writing, you can write these things. A block of ice means a block of mass 5 kg in bracket S equal to 0.1 calorie per gram degree Celsius is heated to 500 degrees Celsius, and kept on large block of ice. Find how much ice will melt. Okay, how much ice will melt? This thing we have to find. A large block of mass 5 kg, specific given 0.1 calorie, is heated to 500 degrees Celsius and kept on the large block of ice. We can say, sir, this is the large block of ice, very large actually. Okay, ice temperature not given, will take 0 degrees Celsius. Here you are keeping this mass 5 kg mass. You know, 5 kg mass is heated. Okay, it is heated to 500 degrees Celsius, and you know that heat will keep on flowing till temperature of block becomes. Heat will keep on flowing till temperature of the block becomes 0 degrees Celsius. Till temperature of the water becomes 0 degree Celsius. Means it will be giving energy 500 to the 0 degree Celsius. It will keep on releasing the energy. How much energy it will release? You can say, sir, in this case, energy release is going to be ms delta theta. This is the energy released by the block. So let's find how much energy it can release. Specific heat always gives you idea what you have to consider for the unit. Specific heat in this question is given 0.1 calorie per gram. Mass we have to take in the gram, and we have to take mass here in the, okay, means mass we are taking in the gram, and energy will be coming in the calorie. So we can say mass, that is given 5. So I will put 5 into 10 power 3 as 0.1. Temperature change from 500 to 0, because it will keep on supplying the energy till the 0 degree Celsius. So we can say this is the energy, and we can say here this becomes actually, okay, 5 and 1 0 here, so it becomes your 250 into 10 power 3. It will be joule or calorie. Of course it is going to be calorie. And why? Because specific heat is, we have to gain 0.1. If specific heat they have given in the joule, then you will do complete question in the joule. You are going to do complete question in the joule. Okay, with this energy, ice will melt or will not melt? You can say, sir, with this energy only ice is going to melt. Ice is going to melt with this energy. And for the melting purpose, we use the formula MLF. So we can say M dash LF, okay, equal to 250 into 10 power 3. So we can say M dash will be equal to this one, 250 into 10 power 3 divided by 80. I'm using 80 because this is the calorie here, okay. So now we can say cancel. So it becomes actually 25 by 8. You can do the conversion here, okay. A gram, okay, this much ice will melt. You can write answer in the kg if required. Okay, geyser with power 2 kilowatt has 84% efficiency. Okay, 84% efficiency. Okay, water flows at rate of 100 cc per second. 100 cc per second if temperature of inlet is 10 degrees Celsius, then find temperature of outlet. Actually, if you see in the geyser, what are the things here? If I say, okay, I can say in the geyser, actually this is the system. Okay, if I say this is the geyser here, so one connection is for the water will be going, and from one water will be coming. This is the inlet and this is the outlet. Okay, from inlet cold temperature, okay, means cold water will be, okay, moving inside, and from outlet we will get hot temperature. The difference is delta theta will be always hot minus, okay, cold, or we can say out minus in. Delta theta is always, okay, out minus in. They are saying 100 cc per second, and you can say, sir, power is given how much? Your 2000 watt. Okay, we can say, sir, usable power, okay, usable power will be how much in this case? 84 by 100 of 2000. So we can say 20 cancel, is 84 into 20. Okay, joule per second is the usable power. Okay, 84 into 20. I'm not multiplying because later on things will be cancelled. I hope you got this part up to this. This is the last question. It is finished. Okay. In calorimetry, after this, you will be able to solve any type of question. Of course, you have to use the brain. Okay. But from my side, whatever the maximum was possible, I have done. Maybe you will, okay, find that in calorimetry, how many questions? If you count how many questions we might have done, probably. Anyone can count and then tell the things. So we can say power is 2000, usable power we can say 84 by 100 into 2000, 84 into 20 joule per second. So we can say how much energy will be there per second. You can say, sir, per second, because this is also given per second. So for 1 second I will take. So you can say, sir, per second it will be 84 into 20 joule. Okay, will be there. And with this energy only temperature will increase. This energy only is going to increase the temperature of the water. So we can say how much here? Your ms delta theta. In this case, what mass I will take? What mass I have to consider? What mass I have to consider in this one? We can say 100 cc. 100 cc means how much? Your 100 gram. Cc means gram, na? Cc means gram, na? So how much mass I have to consider here in this one? 100 gram, okay? And 100 gram is basically your 1 by 10 kg. 1 by 10 kg, na? So we can say, because I'm doing in the joule, means whole question in the SI, okay? So we can say 1 by 10 as 40 to 100, okay, into delta theta will be 84 into 20. So we can say, sir, in this one, let's do 1 0 1 0 cancelled here. One more 0 will be cancelled with this. Here we can say this is the 2, okay? So delta theta becomes in this one, how much? Your 4, okay? Delta theta is your 4. So we can write delta theta will be out, okay? Temperature out minus temperature in equal to 4. In temperature is, okay, 10. So we can say out temperature will be equal to this side. So it will be the 14 degree Celsius. Okay. Yes. Okay. So now, okay, maybe yes, almost, okay, 30-40 questions will be we have done in the calorimetry. There is more than enough for this, okay, small chapter. Now ultimately it depends on your practice. You need to do, okay, so much practice in this one, and okay, think simple all the time. Think simple and then do the things. I hope this question is clear. Yes. Okay. This question is okay, na? And keep your motivation always high, okay? You don't need any external motivation all the time. Which motivation works? Already I said this thing. Which motivation works all the time? Your self-motivation works all the time, okay? So keep that motivation all the time high, okay? And keep on working, okay? Yes? Okay, bye, bye, bye. Okay, enjoy. Yes. And keep on working. Bye. Bye, bye, bye. Okay? Enjoy.